Chapter 2: Rivers and Floodplains. A Montana statute holds that a river has a right to overwhelm its banks and inundate its floodplain. The river has earned it through centuries of deluging and shaping the floodplain, and the floodplain has a right to its rampaging river. Daniel Kemmis. Introduction. A river is a large permanent stream of water originating at a source and flowing along a relatively fixed course, usually into a lake or the sea at its mouth. A creek is a natural stream of water smaller than a river, often a tributary of a river. An arroyo is a water-carved channel or gully in arid country, usually with steep banks, dry most of the time due to infrequent rainfall, unless the gully penetrates below the level of permanent groundwater. The flow can be perennial, interrupted, or ephemeral. A stream channel is a watercourse or conduit carrying water flow under gravity. The water surface profile is sloping and the flow has a noticeable velocity. Depending on its type, the river or stream may include floodplains on the left and right of the channel. Photo 2-1. A stream has a complex three-dimensional geometry and additional properties such as channel roughness. Stream flow is considered perennial, intermittent, or ephemeral. These terms refer to temporal attributes of flow. A perennial stream flows on the surface continuously throughout the year and is considered permanent. The base flow of a perennial stream is maintained by groundwater discharge to the streambed. For this to occur, the water table elevation adjacent to the stream must be higher in some places than the surface water elevation within the stream. Perennial flows can vary widely from year to year and may dry up during severe droughts, although groundwater is generally near the surface. Perennial streams are found in both humid and arid regions, although in arid regions, the reach where the flow becomes perennial generally occurs further downstream, or in places where shallow bedrock forces the water to the surface. Intermittent streams or reaches typically flow for several weeks or months each year when precipitation and associated groundwater inputs are sufficiently high. The timing of the flow and subsequent drying of intermittent streams is broadly predictable on a seasonal basis. An ephemeral stream may be defined as a stream or portion of a stream which flows briefly in direct response to precipitation in the immediate vicinity and whose channel is at all times above the water table elevation. Levick, 2007. Thus, the flow is as unpredictable as the rainfall events that provide water to the stream, which may run for only a few hours or days following a storm of sufficient magnitude to produce overland flow that reaches the channel. Many of the dry washes or arroyos of the more arid regions of North America may be classified as ephemeral streams. Riparian Areas, 2002. Many streams in dryland areas have a spatial attribute known as interrupted flow. Short reaches of perennial flow interspersed between long reaches of ephemeral or intermittent flow. Stream channels naturally meander, and the meandering process eventually results in the evolution of a floodplain adjacent to the channel, except where bedrock, large boulders, a steep valley slope, or human infrastructure prevent floodplain formation. In alluvial valleys, floodplains are desirable because they dissipate flood energies across a relatively wide area, reduce flood peaks as flood flows spread out, facilitate sediment retention, retain groundwater, and provide habitats for streamside vegetation and wildlife. Natural stream function. The lifespan of a stream may be as long or longer than the lifespan of the surrounding mountains. During this time, the stream's function is to convey discharge, dissipate energy, and transport sediment. An important, often overlooked, job of a stream is to carry the mountain, bit by bit to the sea or closed basin. There are 4 basic sources of stream flow. 1. Groundwater flow into the channel provides the base flow, or normal flow of the stream. 2. Interflow from the soil moisture zone that augments base flow. 3. Surface runoff from overland flow contributes to stream flow following storms or snowmelt. And 4. Precipitation falling directly into the channel, an insignificant contributor. Discharge. Stream discharge is the volume of water passing through a particular cross-section per unit of time. In English units, this is measured in cubic feet per second, CFS. Discharge is determined in the field by measuring a stream's velocity at carefully selected points along a cross-section, and then multiplying by the appropriate cross-sectional area. Continuity equation, page 31. The discharge of a perennial flowing stream is provided by the 4 basic sources of stream flow fluctuating with the season and storm events. Ritter, 2006. Energy dissipation. The kinetic energy of a stream flowing downhill is dissipated by roughness, erosion, and sediment transport. Roughness. How fast a stream flows depends in part on what obstacles the water encounters along its path. Roughness creates friction, which converts the kinetic energy of moving water to heat. There are various types of roughness. Relative roughness is caused by particles that stick up into the flow, such as branches, large rocks, vegetation, and variations in channel cross-section. Photo 2-2, Figure 2-3, page 20. Other types of roughness that cause drag include step pools, riffles, and meanders themselves. Photo 2-3. Meanders in a stream slow the flow of water because as the extent of a meander increases, stream length increases and stream slope decreases, therefore decreasing flow velocity. Channel roughness can be calculated from measured values using Manning's equation. Sidebar, Manning's equation. This is an empirical formula for the mean velocity of gravity-driven, uniform, fully developed turbulent flows in rough open channels. It is among the better-known expressions used by hydrologists, geomorphologists, and hydraulic engineers. The formula is customarily used to determine the capacity of natural streams and floodplains, to design artificial channels, and to determine the size of road culverts. Gioia, 2002. Manning's equation. V equals 1.49 times R 2/3 times S half over N, where V equals velocity, feet over S, R equals A over WP equals hydraulic radius, feet, area over wetted perimeter. S equals stream channel slope, feet over feet. N equals Manning's roughness coefficient, feet 1/3 over S. Manning's equation is the most commonly used equation to analyze open channel flows and is a function of velocity, cross-sectional area, wetted perimeter, and channel slope. It is an empirical equation for simulating water flows in channels and culverts where the water is open to the atmosphere, i.e. not flowing under pressure, and was first presented in 1889 by Irish engineer Robert Manning. The channel can be any shape, circular, rectangular, triangular, or irregular. Manning's equation was developed for uniform steady state flow, i.e. when the slope of the water surface is equal to the slope of the bottom of the channel. The hydraulic roughness of the stream also varies as a function of stage, which is embodied in the R term. So this equation has limited usefulness in a live stream. However, N can be computed by measuring the other variables in a live stream. From the table below, the range of Manning's N spans a factor of 6. This is much larger variation than one could hope to get from any other variable in the effort to restore a degraded stream, except for increasing the width of the floodplain. The Manning roughness coefficient is dependent on many factors, including river bottom composition and sinuosity. Often, the best method to estimate N is to use photographs of river channels where N has been determined using Manning's formula. Values typically range between 0.02 and 0.04 for smooth and straight rivers to 0.075 for sinuous rivers and creeks with excess debris on the river bottom or river banks. Figure 2-2. Roughness provided by an object of a given size protruding into the flow is inversely proportional to stream stage depth. The deeper the water gets, the larger the object must be in order to provide significant friction. Photo 2-3. For this reason, sedges growing just below bank full, induced meandering structures, and cobble-sized rocks in a stream provide substantial roughness during a bank-full event, but somewhat less during an overbank flood event. Photo 2-2. A well-vegetated floodplain, a willow stand just above bank full on the floodplain, and large boulders provide roughness during an overbank flood event, but not a bank-full event. Erosion. Erosion is the forced relocation of soil and is a natural process. It is neither good nor bad in and of itself. Sedimentation is the product of erosion. It can be productive or destructive. Deposits can form soil, build new land, bury fields, block culverts, fill ditches, and smother wetlands. Streambank erosion dissipates energy when the force of moving water in the channel is expended while dislodging particles from the bank. Sediment transport. The flow of a stream is not composed only of water. It includes particles the stream is capable of moving that are either delivered to it from the adjacent upstream reaches and tributaries or from its own locally eroding bed and banks. Water flowing in a stream is never pure H2O, but more like a chunky soup. It contains dissolved minerals from the rocks in the watershed and soluble dust and pollution cleaned out of the sky by the rains. This is called dissolved load and can sometimes impart a slight hue to the water. The material that makes water turbid is called wash load. Wash load consists of silt and small clay-sized particles which can take up to several days to settle in still water. The suspended load is composed of sand and sometimes heavier particles scooped off the channel bed by a turbulent mixing process to travel for varying distances before being suddenly dropped, only to be picked up again. Larger particles, gravel, cobble, and boulders are periodically rolled or dragged along the stream bottom by the current or bumped by each other, each according to its size, shape, density, and reactions with the other particles. This material is called bed load. A rule of thumb, many bed load particles begin moving at about 80% of bank full flow. Sediment transport dissipates energy because it takes energy to dislodge, lift, roll, slide, or drag a sediment particle along the stream bottom and keep it in motion. Each time moving particles collide or drag, friction is created and energy is dissipated as heat. Clear-flowing streams that are clean with no sediment load have erosional power to spare. Meandering. Induced meandering works by influencing the pattern of erosion and deposition of sediment within the stream channel. The path taken by a meandering stream channel reveals how energy is being expended by the river and dissipated by the shape of its channel and the flood-prone area. It is evidence of a clash of tremendous forces over time, an interaction between the irresistible force and the immovable object. Compared to a straight reach, a meandering reach has a reduced slope, reduced velocity, and reduced sediment transport capacity, because a stable meander maintains a longer stream length and a greater channel surface area than does a straight reach. The greater channel surface area translates to greater total resistance, effectively dissipating stream energy. As the channel meanders down its valley, the connection between stream flow and alluvial groundwater is maintained as water soaks into the banks. Meanders scroll downstream over time. Along the outside of the meander bends, the downstream 1/3 of each bend experiences the greatest shear stress of any part of the stream channel. Here, erosion of the relatively stable, well-vegetated stream banks happens very slow over time, while deposition on the inside of these bends maintains a constant channel width. During this process, the whole landform scrolls down the valley very, very slowly, yet the stream maintains a similar meander pattern. Bird's eye view. The process is called meander migration or meander scrolling. It is not known for certain why streams naturally meander. It may be a stochastic response to slight irregularities in the banks. The phenomenon of meandering has been observed worldwide on all sizes of streams and has been called the central tendency of streams. Rosgen, 1996. Furthermore, there is a mathematical relationship between channel width and the distance between meanders that holds true for all streams. This relationship is the basis for the layout of an induced meandering project as discussed in Chapter 7. Stratified alluvium. Streams have a natural sorting mechanism for the sediment that makes up their beds and banks. Given enough time, and this is a very long time in relation to a human lifespan, a stream channel meanders very slowly, side to side across its valley, sorting the alluvium as stream bank erosion and deposition occurs. Different patterns of erosion and deposition tend to result in the heavier cobble and gravel-sized particles coming to rest in the lower layers of deposition. Over a very long time, the stream sorts and resorts all the sediment in the valley to the depth of its pools. This sorting process has plenty of randomness, but the result is discernible layering or strata. The largest particles have a higher probability of being placed in the bottom stratum, while smaller particles are deposited in successively higher layers. Where the porous cobble gravel layers intercept the stream channel, the stream is connected with the alluvial aquifer that modulates stream flow. This connection serves as the plumbing infrastructure for sub-irrigating the valley as near-surface groundwater moves horizontally down the valley through the very porous cobble gravel layers. Figure 2-4. Out on the floodplain, where the fine sand, silt, and clay layers are in direct contact with the water flowing through the cobble gravel layers below, capillary action raises water to the upper strata, promoting the growth of riparian vegetation. The maximum height that water can be lifted by capillary action is inversely proportional to the particle size of the bank, i.e., the rise is greater the finer the particle size. For 0.01 millimeter diameter particles, fine clay, the capillary rise is about 55 inches. The capillary rise for a packed bank of 1 millimeter size particles, coarse to very coarse sand, is about a ½ inch. The cobble gravel layer does not clog with wash load because the water flows straight down valley at a slightly steeper gradient than the meandering stream channel. An effective technique for restoring subsurface irrigation of the first terrace in incised channels is to raise the elevation of the riffles in order to place the water surface at base flow back in contact with the cobble gravel layer and to once again saturate the fine textured strata above. During high flows, this contact zone recharges the alluvial aquifer, which later serves to extend base flow by slowly releasing this stored water to the creek. Gordon, 2004. Stream power. Stream power is the ability of a stream to do work against its bed and banks. The weight of the moving water exerts a shear stress, force per unit area equals F/A, pounds per square inch in English units, on the solid particles that make up those surfaces. Stream power is the product of that shear stress and the average velocity, V average, of the stream and is the power per unit area of the stream bed. Thus, stream power equals F/A times V average. Stream power is a function of average velocity, width, and depth, and is a useful index for describing the erosive capacity of streams. Figure 2-5. Gordon, 2004. Velocity is determined by the balance between the gravitational force as a result of the slope of the stream and the expenditure of energy overcoming the frictional resistance of the channel. In general, the velocity is greatest at the center of the channel, just below the surface. The zone of highest velocity tends to follow the stream thalweg, which is a line that connects the deepest parts of the stream channel. Water moving over the thalweg encounters the least resistance to flow, yielding a higher velocity. It is important to know how much power the river has to move its bedload, to erode and deposit sediment. The largest particle that can be moved by a stream at a given stage is called its competency. At a lower velocity, the river has less energy to move sediment. At higher velocity, larger and larger particles become dislodged and move down the stream bed. Figure 2.6 conceptually illustrates stream competency as a function of velocity. Figure 2.7 shows, for example, that 3-foot deep water moving at 4 feet per second will transport 1/4 to 1/2 inch gravel. As the depth and velocity increase, the ability of the river to move its bedload significantly increases. Not only does the competency increase, the total amount of material moving increases as well. The balance of forces. The course of the river is the boundary between an immovable object, the bank, and an irresistible force, the river. During a flood, as water continues to rise and its depth increases, so does its power. When the force becomes more powerful than the immovable object can resist, banks begin to erode. There are many feedback loops that determine the course of the river, but ultimately its course is where it expends the least energy. Accumulating changes of the river tend to be self-correcting over time. For example, an overextended meander can occur naturally, especially if stream banks lack stability. Photo 2-5. If a meander becomes overextended, the channel slope flattens, so the velocity decreases. But since there is still the same discharge coming down the stream, the water pools and becomes deeper until the flow finally overtops and/or breaks through the bank partway through the meander, correcting the overextended meander by cutting off part of the channel. Abandoned meanders can become oxbow lakes, but in arid lands they tend to fill with sediment to the elevation of the floodplain within a short time. The critical role of vegetation. Native riparian vegetation is essential in maintaining stable stream banks. Its role is frequently underestimated or discounted. Vegetation increases roughness, thereby reducing stream velocity and erosion of the soil surface while facilitating deposition and soil building. Vegetation modulates soil and water temperature and reduces water loss to evaporation. Beneficial riparian vegetation is exemplified by the various species of willows. Their many supple stems bend over during flood events and protect the stream banks and floodplains from surface erosion by creating a low-velocity zone right at the surface of the ground. Photo 2-6. In contrast, tamarisk and Russian olive, invasive non-native species, do not bend easily during floods and leave banks exposed to erosion. The many strong roots of willows and other woody riparian species hold firmly to the boulders, cobbles, and gravels of stream banks and thus maintain stable meanders by protecting the banks from lateral scour during flood events. In a perennial or intermittent stream, aquatic vegetation with well-developed root systems can protect the banks sufficiently to maintain the meander pattern. Photo 2-7. In an ephemeral stream, the vegetation is likely to be relatively sparse and dominated by upland species with much lower root densities. Therefore, ephemeral channels tend to be more erodible and have less sinuosity than perennial streams. Photo 2-8. In dryland streams, high levels of available soil oxygen allow tree roots of upland species to grow under the channel, offering protection against bed erosion. Photo 3-4, The Hammock Effect, Chapter 3, page 55. Healthy riparian vegetation can have a significant effect on the flood hydrograph. By maintaining a smaller, narrower stream channel between well-protected banks, riparian vegetation forces overbank flooding to occur more readily as a flood crest rises. Prolonged inundation of the floodplain saturates the ground to increasing depths, promoting infiltration and storing water in the alluvium. Bank storage seeps back to the creek and maintains base flow long after the flood pulse has passed. Temporary storage and release, if allowed to act over a long enough distance, is known to preserve or even recreate perennial flow in stream reaches that would be ephemeral without that vegetation. Government agencies once advocated killing willows with herbicides to increase forage yields and decrease evapotranspiration. Unfortunately, such advice resulted in extensive stream bank erosion and dried up many perennial streams. Groundwater recharge was reduced, as were groundwater storage capacity, sub-irrigation of flood-prone lands, and, ironically, forage yield itself. The water used directly by riparian plants for their own survival is balanced by the services provided to the ecosystem by the plant community. This is qualitatively different from the role of upland woody vegetation, which can become overabundant and desiccate the watershed. Upland vegetation. The above discussion does not apply to woody upland vegetation in the watershed. The phenomenon of vegetation type conversion from grasslands to trees and shrubs is known locally as the woody invasion. It has been blamed by some hydrologists for altered water yield to streams in certain settings. Daboud, 2009. Woody vegetation, which ranges from pinon pine and juniper in the mountains to mesquite in the foothills and creosote brush down in the desert, has deeper roots but offers less surface protection from erosion than the historic grassland vegetation it replaces. Overgrazing by livestock in conjunction with fire suppression has shifted the ecological balance from grasses toward woody vegetation. The shrubs and trees that are now invading the historic grasslands are species that can survive grazing because livestock will not eat them when more palatable vegetation is available. If these are plant species that were historically thinned by wildfire, fire suppression will allow them eventually to dominate the site. Successful reversal of the woody invasion will depend on reversing those land management practices that initially triggered and are now constantly expanding this vegetation type conversion. Photo 2-9, 2-10, page 26. In the uplands, juniper removal, an increase in the herbaceous plant cover, and a reduction of bare ground results in increased infiltration and decreased soil erosion. Within riparian areas, juniper removal points to the opportunity to increase spring flow and move toward a watershed that is functional in its ability to capture, store, and safely release water while providing a site that is productive and capable of being managed for sustainable use. De Boot, 2009. Grazing in riparian areas. The following excerpt from Riparian Forest and Scrubland Community Types of Arizona and New Mexico by Robert Sorrow succinctly summarizes the potentially adverse effects of grazing streamside areas and, by extension, stream stability. Grazing by livestock and wildlife impacts riparian vegetation in two ways: removal and trampling. Removal of vegetation potentially reduces both numbers and biomass of plant species. Grazing can also alter species composition of plant communities. 1. Herbivores may actively select for or against particular plant taxons, and 2. Plants may differ in their vulnerability or tolerance to grazing. Excessive grazing has reduced or eliminated regeneration of many riparian stands. As mature vegetation ages, prevention of seedling establishment leaves an even-aged, non-reproducing vegetative community. Improper livestock use not only directly affects riparian vegetation, but also the physical habitat. Trampling increases soil compaction, contributes to stream bank erosion, decreases water quality, widens and shallows channels, and physically destroys vegetation. The effect of trampling is likely to be most pronounced where livestock are concentrated, as along the margins of streams. Stream banks are particularly susceptible to trampling because of their high moisture content. Unstable stream banks lead to accelerated erosion and elevated in-stream sediment loads. Heavily grazed stream banks are eroded away from the water column, outsloped, have undercut banks eliminated, and have greatly reduced water depth. Fencing and complete exclusion of grazing from riparian ecosystems is often identified as the only livestock grazing strategy capable of rehabilitating damaged stream courses. Sorrow, 1989. However, healthy riparian areas and livestock grazing may or may not be mutually exclusive if grazing is managed properly. Strategies for grazing riparian areas by livestock while maintaining a healthy riparian ecosystem include management-intensive grazing, multi-pasture rotational grazing, and dormant season grazing. Briggs, 1996, Bellows, 2003. A good example is Bear Creek near Brothers, Oregon, which had been grazed by domestic livestock since the late 1800s. Prior to 1976, the area was a single pasture that was grazed from April to September. This strategy depleted streamside vegetation and deeply incised the stream channel, causing it to be unstable and actively eroding. Runoff events contained high volumes of sediment, and summer stream flow was often intermittent and low in quality. The restoration goal along Bear Creek was to restore proper stream function and sustainable ranching. As one part of the project, the grazing regime was changed from season-long to a 3-pasture, late winter, early spring use period, mid-February to April 15th. Over the last 30 years, the Bear Creek riparian area has shown substantial improvement. Overgrazing is a concept that is often misinterpreted by those not directly involved in rangeland management and can be confused with the term severe grazing. Severe grazing removes a high proportion of the plant's leaf in either the growing or non-growing season. In the growing season, this causes a temporary setback in the plant's growth. In the more brittle environments, severe grazing at some time during the year is generally beneficial to most bunched perennial grass plants, and especially those with growth points or buds at their base. Savory, 1999. Overgrazing happens when a plant bitten severely in the growing season gets bitten severely again by any herbivore, wild or domestic, while using energy it has taken from its crown, stem bases, or roots to re-establish leaf. If this pattern is continued, it generally results in the eventual death of the plant. In intermediate stages, it results in reduced production from the plant. Overgrazing occurs at 3 different times. 1, when the plant is exposed to the animals for too many days and they are around to regraze it as it tries to regrow. 2, when animals move away but return too soon and graze the plant again while it is still using stored energy to reform leaf. Or 3, immediately following dormancy, when the plant is growing new leaf from stored energy. Properly managed grazing, Bear Creek, for example, makes use of this understanding of how overgrazing occurs. Management is accomplished by controlling the timing, intensity, and frequency of livestock grazing. Recovery of riparian wetland plants can sometimes be achieved by limiting livestock use to the dormant season only, but often total exclusion is required until plant species diversity and vigor are restored. In many areas of the Southwest, streamside vegetation, vital to stream bank stability, is overgrazed or overbrowsed by some species of wildlife, especially elk, leading to serious bank stability issues. Unfortunately, proper management of wildlife populations and movements to protect riparian areas is more difficult to achieve than the riparian-sensitive management of livestock. Under the present social and political climate, only the fencing of riparian habitats seems to be a realistic option for protection from overuse by wildlife. Riparian ecology, nature's water economy. Shading the water surface and stream banks from the sun with a combination of overarching willow stems and tall, leafy cottonwoods reduces water and soil temperatures during the summer months, which reduces evaporation from both the water surface and the moist ground. Vegetation also moderates wind velocity and reduces the rate of evaporation by curbing air circulation. How a clothes dryer functions is a good analogy. To remove moisture from wet clothes and dry them quickly, a clothes dryer uses a fan to blow hot air at a high velocity through the clothes. Where riparian vegetation, including trees, shrubs, and ground cover, is removed, solar insolation heats the ground and dry air easily circulates across the surface, greatly increasing evaporation rates, performing much like a giant clothes dryer. Well-vegetated, stabilized banks become groundwater infiltration galleries which can extend for miles along healthy stream banks. The vegetation provides natural filtering, improves water quality, modulates flood peaks, and extends base flows. The question is often asked, how much water does riparian vegetation use? It is also important to ask, how much water does riparian vegetation create? Maintaining riparian vegetation is a profitable water investment for the stream because the volume of groundwater infiltration and recharge it facilitates more than compensates for the water used by the plant community for its own survival. How wide must the riparian zone be to provide effective filtration and channel stability? As a rule of thumb, the vegetation zone on each side of the channel should be at least as wide as the bankful width of the channel. Dominant discharge and the bankful channel. To modern-day stream restorationists, the bankful channel is a fundamental concept. A stream's dimensions, discharge, flood frequency and duration, and sediment transport capabilities during a bankful event are some of its most important statistics. Visualize a stream during a typical runoff event, just when the banks are on the verge of becoming overtopped, and the occasional sounds of gravel clacking in the channel can be heard. Photo 2-11, page 28. When the water is at the incipient point of spreading onto the floodplain, the stream is said to be flowing at bank full stage. At bank full stage, the stream is powerful enough to move sediment and to work at eroding unstable stream banks without significantly disturbing stable banks. If the stage increases beyond bank full, overflow from the channel will begin to spill onto the floodplain. This is the definition of a flood. The stream banks define the boundary between the active channel and the floodplain. At the bank full stage, erosion, transportation, and deposition of sediment occur only within the bank full channel. At higher stages, some erosion and deposition also occurs on the floodplain, if there is one. However long it lasts, when the flood finally subsides, the stream flow will diminish to the point that relatively little sediment is moving. Stream-powered erosion and deposition virtually cease until the next time the stream rises. A bank-full flow occurs, on average, once every year or two, and in the intervening period, streamside vegetation will attempt to colonize sediment deposits. Leopold, 1964. Wudyer, 1968. In dryland streams, growth of in-channel vegetation can sometimes influence the path of flood flows, causing the banks to erode or the channel to shift. It is the power of bankful and higher floods to erode and transport sediment that naturally shapes the channel, subject to the moderating influence of riparian vegetation. See Flowing Through the Centuries, page 29. Induced meandering, as a restoration method, can utilize the power and intricate sorting mechanism of floods to help incised streams reshape themselves and build new floodplains. Regional curves. In general, the bigger the watershed and the more it rains, the more sediment will be dragged along the stream channel bottom, and the wider and deeper the bankful channel will become as a result. Field survey data collected from several streams in a specific hydrophysiographic province can be plotted to show how bankful channel dimensions increase as the size of the watershed increases. These plots are called regional curves. Regional curves are plots of attributes, such as bankful channel dimensions and discharge as a function of watershed area. Due to natural variability, there is substantial scatter in the data. Figure 2-8, page 29. Since different stream types have widely different width to depth ratios, the most accurate plot is for bankful cross-sectional area. Chapter 3. If the regional curve data are stratified by stream type, the scatter is reduced. In general, when attempting the problematic task of mathematically modeling wild nature, the more stratified the data, the smaller the error bars become. Bankful cross-sectional area increases with the square foot of the watershed area. For example, if a 160 square mile watershed in eastern Arizona would be expected to have a bankful cross-sectional area of near 60 square feet, then a 40 square mile watershed would be expected to have a bankful cross-sectional area near 30 square feet. Figure 2-8. Looking at the scatter in the data points, the actual range of bankful cross-sectional area for the 40 square mile watershed is 20 to 60 square feet. This apparent discrepancy is explained by Moody. While the relationships presented here characterize the physical functions of a wide variety of stream sizes and types, data from both studies produced inconsistent results from two distinct classes of streams. One, The first was ephemeral sand bed stream channels in the most arid portions of the region. These were generally located in southwest Arizona and the southern and southeastern subregions of New Mexico. These channel beds were mobilized by a wide range of flows, and bankful features were not consistently evident. 2. The second class were very large stream systems, which served to transport water and sediment from a variety of sub-watersheds. Examples of these systems are the main stem of the Gila, Salt, Verde, Little Colorado, and San Pedro rivers in Arizona. While bankful features were consistently evident in these channels, they were not represented by the regional curves presented here. This may be due to the size and complexity of their watersheds and/or the greater distance from precipitation sources in their subwatersheds. Additional work needs to be done to more fully understand these systems. Moody, 2003. Flowing through the centuries. Streams persist for many thousands of years, shaping valleys and gorges as they slowly transport the mountains to the sea or to a closed basin. To get a glimpse of how the stream operates over a longer interval than a human lifespan, consider the range of flows a stream experiences in a period of 100 years. By definition, there will be 100 annual peak flood events, including 20 large flood events that will be exceeded every 5 years, 2 very large floods that are exceeded every 50 years, and so on. By mathematical definition, there will only be a single 100-year flood in the 100-year period of interest. The important question is this: is there such a thing as an effective discharge that does the most channel shaping during the 100-year period? If so, modeling a stream based on this discharge would be simpler than a statistical analysis of the frequencies, durations, and sediment transport tonnages of every single flood. In Figure 2.9, 3 curves are plotted as a function of discharge for our century of interest. The first is sediment transport rate in tons per hour for a given discharge. As the discharge increases, the sediment transport rate rises sharply because larger particles become mobilized. All mobilized particles are moving faster, and increased sediment supply is provided to the stream system from tributaries and from bank erosion. The second curve is flood frequency in hours per century for a given discharge. Note that this curve has a peak closer to the low end of its range because it is dominated by the annual flows. Although each annual flood does not last nearly as long as the flood of the century, the 100 annual flows in the century of interest add up to more cumulative time with the stream flowing at the lower discharge. The third curve is the product of the first 2 as per the formula below the graph. From the unit analysis, the product of the first 2 curves has the units of tons of sediment moved per century. As the graph reveals, there does appear to be an effective discharge that is responsible for the majority of channel shaping. A narrow range of runoff events, somewhat larger than the peak of the flood frequency curve, is doing the bulk of the sediment transport, and therefore channel sculpting, over the century. Most channel shaping over time is done by the largest flood, even though it moves the most sediment per hour during its one-time occurrence. Further analysis reveals that the return interval, and therefore magnitude of the effective discharge as calculated above, is close to the return interval of a bankful flood, as measured in the field. This is how fluvial geomorphologists have established the link between the effective discharge and bankful. In dryland streams, this link can be tenuous due to the high irregularity of storms and runoff events, as discussed in the dominance of bankful discharge in the drylands, page 53. The bankful event is a flood slightly larger than either the annual spring runoff event or the biggest monsoon storm of an average year. It has a return interval of 1 to 2 years, depending on the climate of the region. In a perennial stream between 100-year floods, there is an average interval of 100 years for the vegetation to recover and protect the banks. It is the cumulative effect of all the floods that a stream channel experiences during a specific climate regime that shapes its banks and terraces by erosion and deposition under the guiding influence of the riparian vegetation. By identifying the bankful feature of a stream, we are also identifying the effective discharge responsible for shaping and maintaining the channel over time. Cross-sectional area and the continuity equation. One principle used in the analysis of stream flow is the continuity equation. This principle is derived from the fact that mass is conserved in fluid systems regardless of the channel complexity or direction of flow. More simply stated, if steady flow exists in a channel segment and there are no tributaries or significant seepage into or out of the stream channel, the flow entering the channel segment equals the flow leaving it, i.e., what goes in must come out. When the flow is constant in a reach of channel, the discharge, which is the product of the cross-sectional area and average velocity, will be the same for any two cross-sections within that reach. Therefore, if one cross-section has half the cross-sectional area of the other, the velocity through that cross-section will be twice as fast in order to maintain a constant flow. Figure 2-10. The continuity equation, Q equals A times V. The discharge, Q, passing any point on the stream bank can be thought of as the cross-sectional area, A, times the average velocity, V, through this cross-section. As long as there are no tributaries coming into the reach, no irrigation diversions, minimal transmission loss, no underground springs, and negligible evapotranspiration, the stream discharge will be the same as at a nearby point downstream. Outflow equals inflow. A1 times V1 equals A2 times V2. Example, if a riffle cross-sectional area is 20 square feet with an average velocity of 4 feet per second, F over S, what is the discharge? Q equals 20 feet squared times 4 feet over S equals 80 feet to the third power over S. The discharge is 80 cubic feet per second. Suppose the stream has a very deep pool with an area 40 feet squared. The average velocity through the pool would be Q over A equals V, 80 feet to the third power over S, over 40 feet squared equals 2 feet over S. The water moves slower on the average through a pool than a riffle. Suppose there is a run immediately downstream from this pool where the water is going much faster, say 6 feet per second. The new cross-sectional area can be calculated. Q over V equals A, 80 feet to the third power over S, over 6 feet over S equals 13 feet squared. The velocity increase in the run is responsible for accelerating large sediment particles during a flood, thus keeping the pool cleaned out. As the velocity triples, the cross-sectional area of the flow shrinks to 1/3. The decrease in cross-sectional area is directly proportional to the increase in velocity. Photo 2-12, page 31. Addition of willows along both stream banks provides roughness to slow water down during a flood, causing an increase in the cross-sectional area of the stream. This increases the stream's capacity for overbank flooding, which filters the water as it flows through floodplain vegetation, increases channel storage, and thus reduces the probability of downstream flood damage. Floodplain processes and bank full. It is important to realize that floodplains are often relatively narrow strips of land adjacent to riverbanks and not vast territories. For a stream channel 20 feet wide, a 10-foot wide floodplain on both banks might be considered adequate, depending on the type of stream. See entrenchment ratio, page 47. As will be discussed in this section, a floodplain is a depositional feature formed by the river in the present climate and its associated flood regime. Floodplains are critical for energy dissipation during large floods. During a flood, floodwaters move across the relatively shallow vegetated floodplains, depositing fine-grained sediment. At the downstream end of meander bends, a mixing zone develops between the floodplain and the channel. In such places, the meandering stream narrows the floodplain, forcing overbank flow to return to the main channel. The shallow, slower-moving water from the floodplain recombines with the much faster flow of the deeper channel, and the resultant mixing of the waters reduces the average velocity in the channel. The river is like a truck going down a long grade with the driver periodically touching the brakes on the straightaways to avoid building up dangerous speed through the curves. As the flood gets higher, more area is flooded, and more slow-moving water puts on the brakes when it returns to the main channel, thus regulating the velocity and limiting the erosive power of the current. Natural channels form floodplains during very slow down-valley channel migration. As a river meanders, it creates new point bars that will eventually become new floodplains. Downcut or incised channels form new floodplains when there is alternating bank erosion and sediment deposition. When a meandering stream erodes one bank, the opposite bank will experience deposition from upstream sources, so the channel maintains a roughly constant width. As the stream meanders down the valley, first one bank and then the other is on the outside of a bend where the force of erosion is greatest. Frequently, the eroding bank can become undercut and tends to maintain a vertical or overhanging face during this process. Photo 2-13. Imagine the sediment in the stream bed as being transported by a meandering conveyor belt that is normally at rest, but switches on as the stream increases in depth and power. The floodplain is created by sediment that falls off the sides of this conveyor belt. Each larger particle size tends to move with a higher stream flow, travel at a slower speed than smaller particles, and come to rest sooner as flows diminish. In gravel-bedded streams, all classes of bedload are equally mobile. That is, when sufficient velocity is reached, all bedload sizes are equally likely to be entrained. The complex interaction between the different sized particles can also cause them to move in groups. As the flood subsides, particles come to rest on the stream bed, with the bed looking the same as before, but covered by a different set of particles. New rocks from upstream have replaced those which have traveled downstream. The larger, heavier particles, being entrained lower in the water column, tend to be deposited on a bar on the inside of a curve where the velocity is lower. This forms the lower stratum of a floodplain that over time chases the receding bank, maintaining a relatively constant channel width in the process. Progressively finer sediment, being entrained higher in the water column, is deposited on top of this bar as it builds upward until it reaches the elevation of bankful and streamward to maintain the channel width during this process. The reason the deposition stops at bankful elevation is that normally very little sediment is entrained by the streamflow above bankful stage, and the occasional very large floods are just as likely to scour the floodplain as deposit gravel on it. Where the stream bends, one section of floodplain will end and another will begin on the opposite side of the stream. As the stream meanders, it extends its point bars, which will eventually become floodplain. In the case of an incised channel that has been treated to induce meandering, during floods, point bars form and overbank flows erode the opposite banks. Valley widening occurs with above bank full floods, creating space for a wider floodplain on the concave or outboard bank where a bend intersects the hill slope. During flow events near bankfull, the stream sorts particles by size and deposits them in strata with the coarsest on the bottom of the building floodplain. This ultimately creates the cobble gravel layers that become groundwater recharge galleries and serve to sub-irrigate floodplains at base flow. The surface of these deposits is colonized by vegetation, which holds fine sediments in place. The elevation of the newly forming floodplain is regulated by the dominant discharge and its corresponding sediment regime. Note that the sorting of particles that occurs during the meandering process cannot be duplicated by people or machines during a restoration project that reshapes stream banks. Allowing the stream to do its own excavation work, however, has its advantages in cost as well as the distribution of substrate materials. The stream will be more selective about what it transports than a scoop shovel. Gordon, 2004. Induced meandering causes a stream to erode alternate banks and to build floodplains by naturally eroding, sorting, and depositing sediment by size in the appropriate layers. Meandering is the only process that can recreate the stratified infiltration gallery that is essential for sub-irrigation of floodplain vegetation and regulation of base flow. Where appropriate, putting the stream back into its old channel will likely reconnect it with the pre-existing strata. During the ascending limb of a flood hydrograph, both the velocity and erosive power of the flow increase with the rising flood stage, both reaching a maximum near bankfull stage. Just at the point where the stream begins to flood its banks, the width of the water surface starts increasing much more rapidly than does the depth of the channel. The rapidly widening water surface, combined with the flow resistance offered by vegetation on the floodplain, dissipates the power of the flood and causes a reduction in average velocity. To repeat, the average velocity decreases when a stream floods its banks. This is why well-vegetated, accessible floodplains are so essential to stream channel stability. A stream that has incised its channel no longer has access to a floodplain at the same discharge. Without the moderating effects of a floodplain, as the flood stage rises, velocity and shear stress increase and the rate of bank erosion accelerates.
Figure 2-11, page 34.
In addition to decreasing erosive shear stress, natural flood attenuation is another ecosystem service provided by floodplains. During a flood event, the water level in the channel rises, overtops the stream banks, and spreads out onto the floodplain where a large volume of water is detained. As the flood stage rises along a given stream reach, it takes a considerable volume of water to fill the channel. This is called channel storage. While this is happening, a portion of the stream's inflow is temporarily detained by this dynamic reservoir effect, causing the peak outflow from the reach to be somewhat less than the peak inflow. As the flood wave moves downstream, a greater portion of the water is stored in flooded areas, and the power of the flood is dissipated. Meanwhile, inundation of the floodplain saturates the alluvium where water will be stored, only to seep out to the stream again after the flood subsides, maintaining extended base flow. On a more immediate timescale, as the flood subsides, the inundated areas release their water to the channel, both prolonging the duration of the runoff event and reducing its severity in proportion to how much floodplain area was inundated to what depth and the porosity of the alluvium. Where there is no floodplain because the stream is trapped in a deep gully or has been isolated from its floodplain by levees, The entire flood pulse is conveyed downstream in a very short time, increasing the impacts of the flood and often leaving a dry channel just a few days after the flood passes.
Photo 2-14.
Induced meandering provides an incised channel with a strategically placed set of erosional and depositional surfaces. The energy of a flood pulse is directed towards eroding selected bank segments, and the sediment is transported to point bars in a newly building floodplain. Natural channel formation and stability. A stable stream channel is one formed by the river in the present climate that has the ability to convey its water and sediment load over time without significantly aggrading, degrading, or changing its dimension, pattern, or profile. An apparently stable stream channel is said to be in dynamic equilibrium. A stream channel may be destabilized by many factors, including changes in watershed condition. No channel is needed for rainwater to run off the side of a hill. If the vegetation is in good condition, water moves quite a distance downhill after a rainstorm without scouring a channel. To a large extent, it is not the motion of the water, but the dragging, bumping, and rolling of bedload during concentrated flood events that scours emergent vegetation and sculpts a stream channel through erosion, transportation, and deposition of sediment. Far enough down valley, where the watershed area has increased and the landform has concentrated runoff to the point that occasional flows are powerful enough to move the larger soil particles, a channel will naturally form, the dimensions of which are determined by flood events. In perennial streams, in addition to the flows at bankful stage, there may be smaller flows caused by lesser storms and even a smaller base flow that persists for the rest of the year. The occasional floods of different heights and duration are capable of moving varying amounts of sediment. It is the sum of all flow events, the timing, frequency, and duration of the floods and vegetation growth between floods that shapes the channel. In an ephemeral stream, even lesser flows that are not powerful enough to move sediment have an important role in shaping the channel because the vigor of riparian vegetation is favored by the added moisture. In an apparently stable stream, why does the channel not keep digging deeper without limit? Unless there are headcuts moving upstream, the depth of scour during a flood event is limited by available stream power. Pushing a car through a gravel parking lot is a good example. Even going downhill, it requires a lot of work to move it. Even though the stream bed runs downhill, it takes energy to bump and drag sediment downstream, and this sediment is continually replaced from sources of upstream sediment. The amount of material mobilized and the depth of scour is therefore limited by stream power. Grade control is another reason that streams do not necessarily dig deep channels. Downcutting can be inhibited by bedrock control features, a culvert through a road grade, or any non-changeable elevation in the system. Every stream has a limit to the size of the stone that it can transport, even during its largest flood. Several layers of such stones set into the stream bed would be an effective grade control. Sea level is considered the ultimate grade control for large rivers. There can be bed scour and elevation loss in a stable stream if there is an unusually long flow event at the stage equal to or slightly less than bankful. Remember that the shear stress approaches its maximum just before a stream overtops its banks, so a long duration flood event that is slightly less than bankful stage can be very erosive. Prolonged flows near bankful stage can occur from the gradual melting of deep snowpacks. In some cases, natural levees are formed in high sediment streams during very high flow events. Does overbanking trap a stream between natural levees and cause it to become incised? The answer is that in most cases, natural levees tend to be discontinuous. They are breached in places where water on the floodplain finds its way back into the main channel.
Such gaps allow floodwaters from subsequent floods to access the floodplain behind the levees, which tend to become eroded by smaller, less sediment-laden floods. Also, since bedload sediment is much denser than water, it is transported close to the channel bottom during all but the very largest floods. When very large floods propel large particles from the channel onto the floodplain, these deposits are called terrace gravels. Photo 2-15. Different sized flow events can affect the stream bank differently. Very large floods in a stable stream channel tend to widen the flood-prone area without destroying the existing banks. A stream bank can also be formed at a lower level than the expected floodplain. This feature is called an inner berm. Inner berms are formed by flow events that are below bankful, yet strong enough and long enough in duration to transport and redeposit enough sediment to produce the berms. Prolonged and repeated diversion of seasonal floodwaters for irrigation purposes can result in formation of an inner berm. Perennial dryland streams may also have a distinct base flow channel in addition to a bankful channel. Rapid meander scrolling is a commonly observed phenomenon in the Southwest, but it may not be as natural as one might think. A very large number of streams and arroyos have been distributed by anthropogenic activity. So many, in fact, that it is hard to find a stream that is not in a state of disequilibrium. As a result, many streams are widely scrolling downstream in a way that resembles the smoke patterns of a burning cigarette. This produces excess sediment from the eroding stream banks. In a stable stream, in a healthy watershed with lush riparian vegetation on both banks and a generous floodplain, the rate of downstream meander migration may be too slow to notice during a human lifespan. It is understandable that property boundaries are often established on the faulty belief that river locations are permanent. Geomorphic channel features. A stream channel is a complex three-dimensional shape. On paper, this can be analyzed by looking at three two-dimensional representations: the cross-section, plan view, and longitudinal profile. Cross-section. The cross-section is a cutaway view of the stream channel viewed looking downstream. Figure 2-12. The right and left banks of a river are defined when facing downstream as from a drifting canoe. The terms are river right and river left. Several channel features are described by a cross-section. The thalweg is the line connecting the deepest parts of the channel and means valley way in German. Bankful stage is the water level required to fill the channel to a point above which water would enter the floodplain. Bankful width is the width of the water surface when the stream is flowing at bankful stage. In cases where multiple channels exist, bankful width is the sum of the individual channel widths along the cross-section. The floodplain is the low-lying strip of land adjacent to the bankful channel that is subject to recurring inundation. River terraces are old floodplains that were left high and dry by an incising channel. Lateral erosion of the stream channel and hill slope erosion tend to remove terraces over geologic time. Sometimes a terrace remnant or a narrow remaining piece of terrace is still recognizable. Terraces are numbered starting from the one closest to the present stream bed and going uphill. A terrace cut bank is created where the outside of a meander bend is eroding the toe of the terrace, causing it to maintain a vertical bank. A valley cut bank is created where the river erodes the base of the hill slope. It is not uncommon to discover an abandoned channel on the first or second terrace. Higher terraces may be too old for this type of feature to be preserved because the abandoned channels tend to fill in over time. The dimensions of the old channel, if recently abandoned, may be useful in designing a restoration project in an incised stream system that no longer has a stable channel to model. Plan view. The plan view is the bird's eye view. Several channel features are indicated on the plan view.
Figure 2-13, page 38.
The crossover feature is the straight length of the channel between adjacent bends in the river. Radius of curvature is the radius of a circle that is the closest fit to the particular stream bend under consideration as measured along the center line of the bankful channel.
Chapter 4, figure 4-7, page 78.
A point bar is a bedload deposit formed on the inside of a bend by the floodwaters of a meandering river. Other types of bars that form within the channel include delta, lateral, and mid-channel. A delta bar forms where flows slow at the confluence with a tributary. A lateral bar forms in the crossover and is an indication of sediment overload. A mid-channel bar would displace the thalweg and is an indication that the discharge is not competent to move the sediment or that there is an obstruction in the channel causing sediment to deposit in its lee or shadow. One measure of meandering is sinuosity. Sinuosity is defined as the stream channel length divided by the valley length. It is also equal to the valley slope divided by the stream channel slope. A wavelength is the straight line distance between corresponding parts of consecutive waves in a wave train. A stream's meander length, or meander wavelength, is defined in the same way.
Figure 2-13, page 38.
Meander lengths are found to be 10 to 16 times the bankful channel width in rivers worldwide. Belt width is the width of the belt or envelope within which the stream meanders. It is dictated by valley shape and influenced by floods that scour the terrace walls, widening the flood-prone area of the creek and making more room for meanders to develop thereafter.
Figure 2-13.
A vein or a baffle in an incised channel works directly to increase the belt width of an incised stream. Chapter 7. Longitudinal profile. The longitudinal profile is a means of illustrating how the stream bed loses elevation as it proceeds down the valley. The thalweg is one of the features surveyed for a longitudinal profile that is used to identify and measure bed features such as riffles, runs, pools, and glides.
Figure 2-14.
The water surface at base flow is also surveyed to provide important information such as depth of pools. A riffle is where the water surface at base flow is flowing quickly.
The top of the riffle is where the water surface becomes noticeably steeper. Riffles are the shallowest part of the stream at base flow. The riffle ends at the run where the bed drops off steeply. A run begins where the riffle ends, where the bed starts to drop off steeply into the pool.
At runs, water speeds up in a tail race as it plunges into a pool below and maintains the pool as a scour hole during large floods. The run ends at the top of the pool, where the water surface becomes flatter. The run is the steepest facet slope of a stream bed. In some restoration structures, large boulders are placed on deep footer stones to form the run. This is a good place to control the grade of the stream in a restoration project. A pool begins at the end of the run, where the water surface becomes relatively flat. The pool is the deepest part of a riffle run pool glide sequence. A glide begins where the pool ends. This is where the bed starts to become shallow and there is upwelling of the flow. At the glide, the bed of the stream has an adverse slope. Upwelling during base flow is forcing water to the surface. The glide ends at the top of the next riffle, where the water surface becomes steep again. A glide is encountered during a longitudinal profile survey when it is necessary to walk uphill to get downstream. The riffle, run, pool, glide sequence is a simplified model describing what one would call vertical meanders. However, streams do not always conform to this pattern. There may be compound pools, interminable riffles, or a wide variety of holes and bumps in the longitudinal profile that seem to defy this set of categories. In ephemeral sand bed streams, the pools fill with sand as the stream flow subsides, so these features are not observable after a flood event. During a flood, however, the pools are scoured out again to become important energy dissipators. A head cut, or bed scarp, forms where there is a sudden drop-off in the channel bottom. Water accelerates as it plunges off the ledge, generating turbulence, scouring material from the bed, and undercutting the drop-off.
Figure 2-15, photos 2-16, 2-17, 2-18, page 40.
Runs differ from head cuts because they are followed by a glide, which maintains deep water in an energy-dissipating pool during the flood event. A stable run does not move during a large flood event. After a head cut has moved upstream, the channel is one step deeper than it was before. In an ephemeral stream, head cuts can also progress during the dry season because the vegetation at the brink of a head cut has exposed roots that dry out and die, reducing the erosion protection in this critical location. A head cut is a serious problem for a watercourse and can be difficult to fix. Many Fords and Chevys have been applied to this problem, as well as tires, gabion baskets, old appliances, and other debris, usually with only temporary success because the water eventually finds its way around the repair and the gully continues on its way up the valley again.
Figure 2-16, photo 2-19.
The proper treatment of head cuts is discussed in Chapter 5. Summary. Meandering rivers flowing through alluvial valleys form floodplains as the force of running water erodes, transports, sorts, and redeposits sediments comprising the valley alluvium. While the complex processes at work in shaping the channel and its floodplain are many and variable, they are immutable and predictable. Having a knowledge of the geomorphological and ecological processes furnishes the basis for understanding the concept of induced meandering and provides the confidence to apply the method in the restoration of incised channels.